everyone, I'm Yuri from Shenzhen Group. Today, I want to talk about a critical challenge in our industry, rubber fatigue and heat generation. Anyone who works with the dynamic rubber products like tires or anti-vibration components knows that these two factors are the arch enemies of performance and longevity. So today I want to talk about understanding of the underlying mechanisms and the modern strategies we can use to overcome them. To solve any problems, we must to understand the root cause. Let's look at the molecular level. In a typical carbon black field and a compound, the interaction between the rubber chains and the filler is far from its ideal. Think of it like this. The rubber chains are physically absorbed onto the carbon black surface, and under dynamic stress, they slipped and slide. And the slipping generates friction, and which generates heat, what we call hysteresis loss. This heat, in turn, to attack the very backbone of a vulcanized network, the polysulfide crosslinks. They start to break down in the process we call the reversion. The crosslink density drops, the physical property degrades, and the product's lifespan is cut short. This is a fundamental challenge we have all faced. So what's the solution? The key is to move from a weak physical absorption to a strong, stable interaction. The advanced formulators have been working on coupling agents that act like molecular bridges. The ideal coupling agent needs two functional ends, one that firmly anchored to the surface of carbon blacks, and another one that integrates with the rubber polymer chain. This is where the chemistry gets interesting. The X end can use multiple forces, covalent bonds, hydrogen bonding, ionic interactions to lock onto the surface sites on the carbon black. The Y end, often containing sulfur moieties or double bonds, integrates into the rubber network. This dual action reduces free chain ends, improves the filler dispersion dramatically, and minimizes the chain slippage that causes heat. Now let's see what this means in practice. I will show you some data from our lab, which you can replicate in yours. In a damping application, we can see that a well-designed anti-fatigue agent can reduce the dynamic static stiffness ratio from around 1.4 to 1.3. This is a significant improvement, and it is directly translating to better vibration isolation. In tire compound, the benefits are even broader. We observed the marked reduction in rolling resistance and a significant improvement in the heat agent resistance. The agent helps maintain the crosslink network integrity under heat, fighting reversion and extending the service life. In conclusion, to solve rubber fatigue is about smart molecular design. By enhancing the polymer-filler interaction, we can fundamentally reduce the heat buildup, prevent reversion, and unlock new level of high performance and durability. This approach is becoming standard practice for anyone who is serious about high performance rubber. Shenzhen Group is passionate about advancing rubber science. We publish technical notes and case studies regularly on these topics. If you want to dive deeper or exchange ideas, welcome the conversation.